Let's play a little bit with the singular value decomposition. Let's look at y is equal to a times x. Now, we saw that we can always multiply a vector by the identity. So one thing we can do is we can say, let's take y and let's multiply it by the identity, except that we split the identity into the unitary matrix U times its Hermitian transpose. And let's similarly insert an identity into the middle right here by inserting V times V Hermitian transpose. Okay. That's an identity. That's an identity. Now, we saw that this vector right here, let's call it y hat, is just the vector of coefficients when you view vector y in the orthonormal basis, that is the columns of U. Similarly, this right here is just the vector x, except when viewed in the basis that constitute the columns of V. Right? So now we have that U times y hat is equal to A times V times x hat. We can then multiply both sides by U Hermitian transpose, and what we get is that y hat is just equal to U Hermitian A V x hat. But we recognize this as just the diagonal matrix sigma times x hat. So what does that mean? What it means is that when given the matrix A, if we view the input vector x and the output vector y in the correct bases, namely we use the columns of U as the basis in which we view y, and we use the columns of V as the basis in which we view x, then our matrix all of a sudden becomes a diagonal matrix. Well, it might be rectangular, but you know what I mean. There are only non-zeros on the primary diagonal of the matrix. And that's really interesting. So, yet another very important insight from the singular value decomposition. It tells you in what basis you perhaps should view vectors.